Dear SPRi, and thank you for everybody for being here. Today I will talk about software safety integrity and software systematic capability in process industry. My name is Amir Moutameni. I work as lead safety engineer for Honeywell Process Solution. In past 20 years, I've been involved in different fields of process automation, including project engineering to project management, project engineering management, and my work is now about functional safety and management of functional safety. This will be the summary of my presentation today. I start to overview of failure and failure types. Then I will introduce the IEC 61508 and 61511 standards. Based on these two standards, I will go through definition of safety integrity, systematic capability, management of software safety integrity, system safety lifecycle, software safety lifecycle, software systematic capability, and we will end up with management of functional safety. Failure and overview of failure types. Failure is the state or condition of not meeting a desirable or intended function. This is a definition of failure by Wikipedia. Failure types. A system may fail to function as required due to either random failure or systematic failure. My presentation today is about systematic failure and how we can avoid and control systematic failure. What is random failure? Random failure is related to the hardware components. It's due to physical cause. Also occurs due to various random events such as abnormal process conditions, corrosion, thermal stressing, wear out, tear out, low frequency atmospheric event. It has no pattern. It, of course, is random. And most important characteristic of random failure is quantified. If your vessel ruptures due to pressure or corrosion is an example of random failure. Systematic failure, however, is due to deterministic way to a root cause. It's caused by human error during design, specification, development, manufacture, installation, operation, maintenance, or decommissioning. Systematic failure has pattern. It's impossible to analyze in a probabilistic manner, is not considered in the verification calculation. It's not part of PFD calculation, probability of failure on demand calculation. And it cannot be quantified. We'll talk about this one more. Since this cannot be quantified, it cannot be engineered and resolved with an engineering solution. This is an example of systematic failure. If you have a machine to shoot to disable, if all of those guys goes to that corner, that means you have a systematic failure in your machine. I want to show you two studies about the systematic failure versus the random failure, and they share about the process industry's accidents. First study has been done by Angel Castle in 2011. In this paper, He went through 35 major incidents between 1987 and 2012. And his studies shows 90% of those accidents happened because of systematic failure. The other 10% is not, he couldn't find the cause, the root cause, but at least 90% of the accident was because of systematic. The other very famous study has been done by HSE UK in second edition of this book, Out of Control, Why Control Systems Go Wrong and How to Prevent Failure. They analyzed 34 incidents based on 56 causes. And based on their research, all of those accidents happened because of systematic failure. All of these shares is type of systematic failure: specification error, design, installation, operation, and change after commissioning. International Electrotechnical Commission, or IEC, in end of 20th century, 1998, they come up with this standard: functional safety of electrical, electronic, and programmable electronic safety-related system, IEC 61508. And the reason this standard, before that, many countries, they had their own standard for safety. But they needed it all together and have a unique standard for every industry and in every country. So this standard was a national evolution for the need to reduce process risk and improve safety through a more formalized and quantifiable methodology. Specifically for IEC 61508, they were needed because the application and software implemented system like PLCs, like all programmable system with the software, they were in the market and they had to be a standard and a formalized way to prove the safety of the systems in all industry, and be as a standard available. To base of that, the engineers can claim that their system are safe enough. IEC 61508 is a blanket standard, like an umbrella. Different industry, they develop their own standard, like railway systems 50128, or machinery, nuclear industry. I don't know if there is any standard for medical industries. I don't know the number. But we will talk about IEC 61511, which is for process industry. IEC 61511 is same as ISA 84. There are minor differences they have, but generally they are the same. IEC 61508 comes up with some definition. First of all, I want to talk about safety integrity. All the requirement about the safety and the standard safety is to reduce the risk of hazardous event. For the hazardous event, we need to do, to reduce the risk of hazardous event, we need to do first a risk assessment on all of the calculation related to that. And finally, we will reach to a requirement for how much, because we cannot make the risk zero. There always will be a risk. But how much risk reduction is required? Based off that, how much safety integrity we need. This is the definition of safety integrity by IEC 6511, version 2016. Average probability of a safety instrumented system satisfactorily performing the requirement safety instrumented function under all the stated conditions within the stated period of time. So safety integrity is all about the probability of functioning when is required in a stated condition and period of time. Safety integrity comprises of hardware safety integrity, which is related to random failure. We had two types of failure. We need to take care of both of them. And systematic safety integrity, including software safety integrity, which will be part of the systematic safety integrity, this one is related to the systematic failures. Let's take a look at a very normal safety instrumented function. Start with the sensors, logic solver like PLC, DCS, or whatever, and final elements. When we say systematic integrity is about whole system, all of them, same as hardware integrity. But the software integrity is about only the logic solver part of the system, like the PLC. Systematic safety integrity. Systematic safety integrity and software safety integrity is to do with the management of systematic failure. Again, I want to repeat that. That is all about the management, how we manage the systematic failures. Again, another definition by 511 about software safety integrity is part of the safety integrity of a safety-related system related to the systematic failure and a dangerous mode of failure that are attributed to software. When we say dangerous mode of failure, I need just to note you that when we talk about functional safety, we work only about dangerous mode of failure. The other type of failure which are not dangerous, we will take care of that during the quality assurance and like other in the industry, how they prove their availability and reliability of their system. Dangerous mode of failure as an example, for example, if you want to go to your work in the morning time and you start your car and car doesn't start, this is a failure, but it's a safe mode of failure. It's nothing happening. But if you are driving on a highway and you push the brake pedal and that doesn't work, this is the example of dangerous failure. When we talk about functional safety, we are talking about only dangerous failure and dangerous failure rate. Okay, safety integrity is a scale for safety, for functional safety. It needs a level. We need a level for this scale since we need different levels of risk reduction. For different levels of risk reduction, we'll have different level of safety integrity. Safety integrity level, or SEAL, is about that how much risk reduction is required. 4 levels of safety integrity has been defined and introduced by 6150L from SEAL 1 to SEAL 4. As per standard, the requirement for SEAL X is hardware safety integrity level X and systematic safety integrity level X. Hardware safety integrity is about architectural constraint like hardware fault tolerant and redundancy. and quantifying the effect of random failure, like probability of failure on demand, proof time interval, mean time to repair, and stuff like that. All is engineering matters about that system. But at the same time, we need a systematic safety integrity in the same level. If we forget that part, half of a story is lost. Systematic safety integrity level X requires systematic capability, same level X. This is another definition by IEC 61508. Systematic safety integrity of an element meets requirement of the specified seal. This is the definition of systematic capability. Is determined the reference to the requirement for the avoidance and control of systematic faults. Just like seal, systematic capability measure on a scale of 1 to 4. Seal X requires systematic capability X. Like I said, a software systematic capability is part of the systematic capability. So the software systematic capability should be in the same level of seal. Achieving of systematic capability. Standards introduced 3 routes. Route 3S is a compliance with the requirement of IEC 61508 for pre-existing software element only. This is a shortcut when you have a pre-existing software in an old system, like you have a legacy PLC or any system with the software. You want to use that software in the new system or new PLC. And you have a good data about the failure rate and operation time and everything as per the requirement has been defined in the standard. You can use this route as a shortcut because the general route, we will see that is really long and complicated. Route 2S is compliance with the requirement for the evidence that the equipment is proven in use. Let's say you have a product in the market, like a transmitter is working for 10 years in the market. You have, again, the failure rate and operation time and every information in all the industries being used. You can use those data to prove your systematic capability of your product. Again, this is another shortcut. Or even if you have a procedure to develop your software or system, you can use this shortcut to prove the systematic capability of your product. But the main way to improve and approve systematic capability is route 1S, compliance with the requirement for the first avoidance of systematic fault and requirement for the control of the systematic faults. We go a little bit through this route 1S, which is the main route for achieving systematic capability. One route for route S, 1S, a standard defined gives us techniques and measure for avoidance of the systematic faults and also for the control of systematic faults. For avoidance of the systematic faults, these are the techniques and measures being introduced. Techniques and measures to avoid mistake during specification of system design requirement. Techniques and measures to avoid introducing fault during system design and development, during system integration, during system operation, and during system safety validation. These are the techniques and measures we need to proceed for avoidance of systematic faults. And table A15 to 17 is about control of systematic faults. Techniques and measure to control systematic failure caused by hardware design, caused by stress or environmental stress or influences, and systematic operational failures. Just to give you an idea, I brought the table here. I'm not going to through them one by one, just to show you. This is the table B1, techniques and measure to avoid mistake during a specification of an electrical, and programmable electronic system during design requirements. These are the techniques and measures, and detail of these techniques can be found here. It's been referred, and depends of what is your safety integrity level. You have recommendations here. For example, project management. For SIL1 is mandatory, and effectiveness of that is low, medium, and high for SIL1 to 4. In this table, you see part of these techniques and measures comes with a white column in the left, and some of them with the gray. The white one, all of them has to be mandatory, is to be implemented. For the gray one, you can pick one, a minimum one, as per your application and your system is required. It's up to you, but you need to have at least one. This is table B1. B2 about the design and development. B3, B4, B5. And B6 is about the effectiveness of each of these techniques and measures. And table A15 for the control of systematic failure during the hardware design. Table A16, 17, and table 18 is about, again, effectiveness of each of these techniques and methods. Again, just to show you how it works, that project management, which was the first technique and measure, these are the description of requirement for the project management if you are working on a functional safety project. Management of software integrity, about the software. Techniques and measure, again, being introduced by 61508. Table A1 to A10 are the techniques and measures. And we have a detailed table about management of the software integrity. Again, in the appendix B, table B1 to B9. Table A1, software safety requirement specification. These are techniques and measure has to be used. Okay, and these are the tables for the software integrity, technique and measure for the detailed table. Okay, again, we go back to the standard 61508. Technical requirements been defined in part 1 to 7 in 508. Part 3 is about the software requirement. This is the overall life cycle by 61508 about the whole life cycle of a project, including at least one safety instrumented function. Part 10 is about, again, EEEP system and development of those systems. Part 10 has his own life cycle to develop the system for the hardware part and systematic failure of the hardware part, and his software safety lifecycle, again for that part 10. This one brings us to very famous V model, which is software safety capability and development lifecycle. This is the lifecycle we need to proceed to develop our software. Based off the safety requirement system, which is for whole safety instrumented function, we need to develop software safety requirement specification. This one is a very main document and the most important one. This document brings us to software architecture. The output of, can be an output of this document, has to be verified, this document, based off safety requirement specification, software system design, model design, coding, model testing, integration testing, and so on. And finally, we need to validate our output, our final software, based on software safety requirement specification. As we see, avoidance and control of systematic faults are significantly more difficult in compared to random failures. A standard defined life cycle to be proceed for to achieve systematic capability of the functional safety systems. To proceed that safety life cycle, we need functional safety planning. Every life cycle needs to be planned. And for that, we need management of functional safety to manage all of this planning and safety life cycle. A different part of the safety life cycle, different parts can be responsible, but finally the end user is responsible for the safety of the system. Overall, it's always end user. Give you a fast example, end user who needs to buy equipment for his safety system. For the seal-rated sensor and final element, they go and buy the certified device, like certified transmitter, certified valve, and stuff like that. But for the logic solver, it's not possible. You can buy certified logic solver like PLC with certified component, like certified module or certified processor, stuff like that. But the whole system cannot be certified because it's been developed for your specific project. The only thing you need to follow is you need to make sure who is developing that system for you. They have functional safety management certificate, that organization. And they have procedure and management and planning based off the standard to proceed that. Just as an example, this is a certification you have for a level transmitter here. It shows you the systematic capability is 3, it's good for SIL 3. And for the random failure, they came for SIL 2 for HFT 0 or so on. And for the functional safety management, same, you have certification companies like TUV, which give functional safety management certificate to the organization who is working for or with functional safety. Thank you.